Hi, so first I would like to thank the organizers for considering me suitable for this task. And so what I'll do is that I talk on the chapter 10 of this book by Britson and Hepfliger. So it is on geometry of SLNR mod SONR. So in the afternoon session, Pralay Chatterjee will speak on more general symmetric spaces. So here we'll work with a particular very special symmetric space. And we'll try to do everything by hand. And so the target is that we get a better understanding of this very particular example, which is very important. So first I will introduce the notations and so on. So, so this is the title of this thing. So first I fix these notations. So M in R. So this is the space of matrices, n cross n matrices. Okay, and so note that it has this natural inner product on this. So this will always denote this natural inner product on this, namely trace of A times B transpose. So it's a vector space of dimension n square, and it has this natural inner product. And inside this GLN R is the group of invertible matrices. So determinant is non-zero. So this is a group, and GLN R plus for me will denote the subgroup of this group where the determinant is positive. This one, and further the subgroup of this one is SLN R, which is matrices with determinant 1. This is subgroup. So this defines this SLN, and SON is a subgroup of SLN R. Special orthogonal matrices, which says that A times A transpose is identity. Like this. So this defines this thing for us, SLN mod SON. And by SNR, I denote the space of symmetric matrices. So all matrices in M and R such that A equal to A transpose. This one. And by putting a 0, I'll denote all matrices in SNR, symmetric matrices, whose trace is 0. Like this. And next I define this PNR. PNR will denote the space of all symmetric matrices such that it is positive definite. Positive definite. So recall that this means that for all vector V inside Rn, we'll have that V dot AV. So this is positive. Okay. And also, yeah, so maybe I should recall that this means that the inner product of V and AW is equal to AV dot AW. So for all VW in Rn for symmetric matrices. This is PNR, and PNR1, so this is subspace of uh, all positive definite symmetric matrices, such that the determinant is 1. So I'll just say that this is PNR intersection SLNR. Okay, and yeah, so now you notice that so you want to study this. So what I'll do is that basically we will concentrate on P and R, and so we'll naturally identify with GLN R mod ON. So I have not defined ON here. So ON is all GLN matrices whose which satisfies this A transpose orthogonal matrices. So now, yeah. So note that this positive definite symmetric matrices. This is so note that P and R is an open subset of SNR, and SNR is a subspace of this all matrices. So therefore, naturally, PNR has a differentiable manifold structure. So hence, PNR is naturally a differentiable manifold. Okay, and so now here's a small lemma. The following will define a group action of GLNR on PNR. So say small g is in GLNR, and you have some P in here. So you send it to GPG transpose. So I just say that, yeah. So this defines a group action of GLNR on PNR. And this action is transitive. And the stabilizer of identity, so identity matrix is an element in PNR, and the stabilizer of identity is ONR. I have not defined ONR, so yeah, so this is the set of all matrices in GLN. So that A transpose is 1. So I indicate a proof briefly. So I just leave for you to check that this is a group action, and then the stabilizer of identity is very clear. Just I have to check that this is transitive. So for that, what you do is that so I have to use the fact that so for all matrix in PNR, you can find there exists another matrix O inside ONR. That you can take SONR, such that when I conjugate this, then this is a diagonal matrix. So this is same thing as saying that this is diagonal. So this is already a matrix in PNR. This is diagonal, and therefore it will follow that with positive entries. Diagonal entries are positive. Okay. So let's say I call it D. So let D be equal to this O inverse. So then this implies that A is O inverse PO, and since this has D has positive entries on the diagonal in the square root, so therefore just take so let G be equal to O inverse square root of D. That means take the positive square root of all the entries on this. Okay, so then this implies then clearly that so G is equal to G transpose, and A is simply G times G, so G transpose. So therefore, this is G times identity times G transpose. Every matrix is in the orbit of identity element. So this proves that this is transitive action. This is transitive. Okay. So now, note that there are some remarks. So note that in fact the proof shows that in fact GLN R plus action is transitive because this G has positive determinant, this one. And also notice that proof implies that PNR is connected. Because you see that so the diagonal matrices, this is because the diagonal matrices with positive entries are already inside this thing, PNR, and this space, the space of diagonal matrices with positive entry, this is connected, and given any matrix I can conjugate it by some SONR matrix such that it belongs to this, but that will fix identity. So therefore this proves that PNR is connected. So PNR is a nice connected manifold, and it has a GLNR action also by diffeomorphisms. And so now also note that as a corollary you can check that so PNR1, the positive definite matrices with determinant 1, this is stable under the action of SLNR. Just go through the proof and you will see that this is stable under SLNR, and this SLNR action, this is again transitive. The same proof will show this is transitive, and the stabilizer of identity which is inside this space is SONR. Okay. So therefore, this PNR1 can be naturally identified with SLNR mod SONR. After some time, we'll define a Riemannian metric on this space, and then you will see that this PNR1 is sitting inside this. So we'll define the metric on PNR, and you will see that this is GLNR invariant, and this PNR1 is a totally geodesic submanifold of this one. And so therefore, SLNR is acting transitively on PNR1 by isometries. Okay, so you can therefore naturally identify PNR1 as SLNR mod SONR. Okay, so therefore PNR1 is giving a model geometry for SLNR mod SONR. So basically, therefore, we concentrate on this to understand SLNR mod SONR. We'll just define a metric on this, and then we'll try to understand what is the restriction on PNR1. Okay. So now, yeah. So I have, Actually, I given a proof. So maybe this is. I'll just leave this as an exercise. So this is very simple. Okay. So now we'll go to the Riemannian metric. Riemannian metric on PNR. Okay. So as I said, so PNR is sitting inside SN R as an open subset, and SN R is a Euclidean space, right? So therefore, it has a differential manifold structure, connected differential manifold structure, and so therefore, you see that note that for all point P inside PNR, the tangent space at this point can be naturally identified with the symmetric matrices. Okay, since it's the open subset of an Euclidean space, you can actually add, right? So now what you do is that you define for all tangent vectors at this point P. So you define this the inner product of x and y. Simply you define it to be the trace of this P inverse x times P inverse y. So at the point P, this is the inner product. So check that. So this check that this defines a smoothly varying symmetric bilinear form on each tangent space. On the tangent spaces of this PNR. Okay? This is not difficult to see that this is smooth. What is not clear is that this is positive definite from tangent spaces of PNR. So we'll check that this is a positive definite. So for that, I just write this as a proposition or something. The GLNR action, so notice that preserves this form. So in other words, if we could already check that this is a positive definite, so it would become a Riemannian matrix. So GLN action is by isometries. So GLNR action preserves this form. So proof. So let P be some point inside this PNR, and suppose I have some GLNR element G. So now you want to understand what is happening to the differential of G. So this is at x P, and so this is happening at G dot P. So this is the action G dot P. So you want to understand this one. So so now notice that this action, when I fix my G, then the action is actually defined on the whole of SLN-R, and it's a linear map. And so therefore this becomes Gx G transpose. This one, sorry, this is Y. So for xy, I am taking inside the tangent space of PNR at P. Okay, so this one, and then this one is GY G transpose, and this is happening at G dot P. Okay, since once I fix my G, so this map x going to Gx, what is that? P going to GP G transpose, that's a linear map on SLN-R. So therefore the differential is very simple to compute. So now this one, we know how to compute this because we defined this inner product here. So therefore this becomes the trace of G dot P inverse times Gx G transpose times G dot P inverse Gy G transpose. This one. And then we'll use the definition of the action. So this is therefore GPG transpose inverse, and then GXG transpose, and then GPG transpose inverse, and GYG transpose. So if you simplify this, then this becomes, so there will be some cancellation. So then finally you will get trace of G transpose inverse, and then X, right? And then you should get a P inverse, this, P inverse Y, P inverse G transpose, like this. Okay. So then we know the conjugate matrices have same trace, so therefore this is equal to trace of X P inverse Y P inverse, like this, and then again conjugate by P inverse. So then this becomes trace of P inverse X P inverse Y. What is that? P4 X? That's what you get here. So when you simplify this one, this becomes like this. Inside this. Acha, sorry. Oh, okay, yeah, sorry. So here you get a P inverse, I guess. I see. There is nothing here you are saying. Oh, you are already done. Yeah, sorry. Thank you. Yeah, now it's fine. So therefore, this is equal to the original thing that started. So inner product of X, Y. Okay. So therefore, the action preserves this form, symmetric bilinear form. And so just now notice that this form is a positive definite at identity. So note that this form is positive definite on this tangent space at identity. Okay. So because what is this? So, so it's very clear. So for all x, y inside the tangent space at identity, so this will be so identity inverse x, identity trace of that, right? So this is therefore trace of x, y. What since x, y asymmetric matrices, I can write this as x, y transpose. So this is a restriction of this form on M in R. So naturally, so for instance, x inner product x is simply x trace of x times x transpose. That is positive. So this is positive definite. So clearly, so therefore this defines a Riemannian metric on PNR, and the G ln R action is by isometrics. Okay. So this proves this. Yeah. So what is the inner product you are taking on the whole of this? The usual inner product? No. Now what is the action? Same action? No, then it will not be, right? So take some scalar matrix maybe. Is not. So G times G transpose, that will multiply, no? So that's there, and then so then yeah. Then we'll define symmetric space, and then we'll check that this PNR is a symmetric space. So what is a symmetric space? For me, so a symmetric space M is a connected Riemannian manifold. Manifold such that for all point P inside M, there is an isometry. Isometry of sigma P from M to M, such that this fixes this point P. Sigma P of P is P, and the differential of this at the point P, the d sigma P at the point P is simply minus identity. It is reversing the directions of all the tangent vectors. So this is symmetric space. So now we plan to check that PNR is a symmetric space. Okay, we'll check that. Theorem: PNR with this Riemannian metric is a symmetric space. Okay, PNR is a symmetric space. So how do I check this? So I have to define this maps for you. So what is this map? So for all point P inside PNR, so what you do is that define sigma P from PNR to PNR by setting Q going to P, Q inverse P, like this. Okay, so we have to check that this is an isometry, and then we have to check that it satisfies those two properties. So yeah, so even before that I have to check that this is already inside PNR. So PQ are inside PNR, and why this? So note that this is a sigma P is the composition of these two mass. One is Q going to Q inverse, and the other one is the action, that is you send Q to PQ P transpose. So PNR is naturally a subset of GLNR, so GLNR acts by isometry checked. So this one, but this is same thing as, since this is symmetric. So first we apply this one, and then apply this one. So this is already an isometry, we know that. So therefore we have to check this is an isometry, that you will check that sigma P is an isometry, and then you have to compute the differential. So clearly this fixes the point P also. Okay. So therefore we have to check that this Q going to Q inverse, that is okay. So claim therefore this I'll denote this by tau. So Q going to Q inverse. So this one now is easy to check. So this is landing inside PNR. So once I take Q to in PNR, this is in PNR. So this is a well-defined map. So and then I'll check that this is an isometry. This is a smooth map, and to check that this is an isometry. So what do I do for that? Is that so you fix any point, and then so fix a point. So you should not confuse this point P with the other one. So yes, maybe fix a point P inside PNR. Maybe I should say Q. P is already fixed. So fix a point Q, and a tangent vector, let's say X, inside the tangent space. Okay. So then let alpha be the curve T going to Q plus Tx. So this is naturally identified with the symmetric matrices. Right. So therefore, since PNR is sitting inside SNR, for small values of t, this is inside PNR. So this is a curve for small values of t less than equal to mod t less than equal to epsilon, something like that. Open interval around 0, 1. This will be inside PNR. So note that then this is a curve passing through Q. So alpha of 0 equal to Q, and alpha prime 0, the derivative is x. So this is a curve inside PNR, and its tangent vector is x at the point Q. Okay, so then what you do is that so let us compute this differential. I mean take the derivative of this map tau at the point Q and see where x is going. So we'll check that. So the derivative of tau at the point Q acting on x. So this is equal to the tangent vector at Q inverse to the curve. So we just take this curve and apply the map tau. So therefore, t going to Q plus tx inverse. Okay. So just we need to check what is the derivative of this function Q plus tx inverse at t equal to 0. Like this. Okay. So to do this, so I'll just after this, what I'll do is that I just use some approximation to this one. So, but of course, you can make this rigorous also. So Q plus tx inverse. This one I'll compute like this. So I take. So this is a matrix in PNR. So I'll do Q times 1 plus t times Q inverse x whole inverse, and so this then turns out to be 1 plus t Q inverse x inverse times Q inverse, like this. And then for very small values of t close to 0, then this is 1 minus this thing, Q inverse. This is where I am not very careful, but you can make it very rigorous proof. Just leave that for you to check. So, t times Q inverse x, like this. Okay. So this means that hence this derivative, hence the derivative at Q on x is simply minus Q inverse x Q inverse, like this. This is the derivative. And then once we have the derivative, then to check isometry, just take the inner product of this kind of two things and then do it. So therefore, hence for all tangent vectors xy at the point Q, I take the inner product of this this one, and this is happening at Q inverse. Okay, and so this is the same thing as so there is a minus sign. I just neglect the minus sign, right? So Q inverse x Q inverse, then Q inverse y Q inverse, like this. And so therefore this becomes recall, so inner product was trace of P inverse x P inverse y. So therefore, this is Q times Q inverse X Q inverse, and then Q times Q inverse Y Q inverse. Sorry, trace of that. Okay. So this one cancels and this one cancels. So therefore, you get trace of X Q inverse Y Q inverse. Okay. And then use that fact that trace of AB is equal to trace of BA, like that. So this is A, this is B. So therefore, this is equal to trace of Q inverse X Q inverse Y. So this is the inner product of X, Y at Q. So this proves that this tau is an isometry. Is it okay? This proves that this is an isometry. And then I have to check that this reverses the direction of the geodesics. That part I still have to check. So let AP denote the map. So Q going to PQ P transpose, that is PQP. So then already I said that so this sigma P is first you apply tau and then apply AP. So you want to check that the differential of this on X is minus X. You have to check that. So let's check that. So at P I have to check. So derivative of sigma P at P from some point X. So for all X in the tangent vector, tangent space, this is the same thing as AP compose tau and this is the same thing as the derivative of AP at tau P, that is P inverse, and then derivative of tau at P on X. Chain rule. And this one we have computed already. So this is minus P inverse X P inverse. This one we computed just now. And again I say that AP, you can, so this is defined on the whole of S in R. It's a linear map. So then it is easy to compute. So therefore this is equal to minus, just you have to multiply by, what was this? P on the both sides. So multiply P on the both sides of this. Minus X as required. Okay. So therefore this proves that sigma P is an isometry which reverses the directions of geodesics. Okay. It proves for me that this is a symmetric space. Is it okay so far? So I'll make some remark now that yeah, so maybe this is just a terminology. So number one, you notice that the isometries of this type sigma P compose sigma P1 for two matrices P, P1 inside PNR. These are called transvections. So one can check that this isometry will fix the geodesic line through P and P1 and it acts by translation. So I'm not going to check that. So in particular, sigma identity compose sigma P. Okay, so this sigma identity compose sigma P. This is a very special. No, I just wanted to see other way around. So this one is what? So first this one goes to Q inverse and then take the inverse of that. So this PQP. This one, this is a transaction. So this is simply AP, as I defined sometimes back. So AP. So AP was this coming from the GLNR action. So this that was a transaction. Okay. And remark number 2 is that you notice that is to check that if P is already inside PNR minus 1, PNR 1, the subspace of PNR, which contains the determinant 1 matrices, then sigma P of PNR 1 is PNR 1. Okay, so this proves that when I restrict my Riemannian metric from PNR to PNR 1, then PNR 1 becomes a symmetric space on its own right. Okay. Yeah, of course I have to say that. Then, hence it follows that PNR 1 is a symmetric space with the Riemannian metric restricted from PNR. Okay. So of course I have not said that why it is a manifold. First of all, so it is not very difficult to show, because what you can do is that you take the determinant map from PNR to positive real numbers, and then this is simply the inverse image of 1, and you show that 1 is a regular value for this map. This is not very difficult to show, so I'll just skip that. Okay, make sense? Okay, so next goal is that so PNR is a symmetric space, nice space. So next goal is to understand more about the geometry of this one. So next goal for us is that we'll try to put that PNR is a cat 0 space. Okay. So if you have not already seen what it is, so basically we are trying to show that it is equivalent that this has non-positive curvature. So this is what we are trying to show. So for that I had to so I'll take a break. I mean, in the sense that take some I'll take a break to do some elementary calculations with matrices for some time. It may be boring, but after that it will follow that eventually we will prove that this is a cat 0 space. So I'll recall some basic facts. About the exponential map from MNR to GLNR. So I'll state this as a lemma. Lemma 1 is that if I take the exponential of A transpose, then that is the same thing as first take exponential and then transpose. This one. And then if A be commute, then follows that exponential of A times exponential of B is exponential of A plus B. So these are all very elementary things, and mostly I will not prove them. In particular, exponential of minus A is the inverse of exponential A. This one. And then if I conjugate by some matrix inside GL and R, yeah, I am not being very precise here. Here, this A, B, these are inside the matrix, any matrix. This is exponential of G, A, G inverse. You can put it inside the exponential. And then the derivative, derivative of this map, T going to exponential TA is A times exponential TA. So all this 1, 2, 3, 4, they are all very easy to prove. So exponential map is smooth. This is also very standard. Okay, and lastly, so exponential map. So this is something to do with PNRs. Exponential map from maps symmetric matrices bijectively onto PNR, and it maps Sn R0, that is the trace zero matrices inside this, bijectively onto PNR1. PNR1. This is what I will try to show. Okay, so in fact, this map, exponential map from SNR to PNR is a diffeomorphism. This is quite standard, so I will not prove this. Suppose I don't remember a proof, but maybe we'll see some indirect proof next time. So proof. So 1, 2, 3, 4, these are easy. 5 is standard, and 6 I'll try to prove. Yeah, so here I am just trying to prove that it's a bijection, so but it's actually a diffeomorphism. Yeah, so what do I do? So this will follow from several standard facts about the symmetric positive defining matrices. So one thing is that, as I said, so, since we have already stated that, so for all P inside PNR, there exists so in fact, even before that, so if I take some symmetric matrix, then there exists an orthogonal matrix O such that it diagonalizes this, so such that O inverse is diagonal. Okay, and then you apply this lemma part is that free, and so then it will follow that. So this implies that exponential of Sn is actually inside Pn. Okay, so it is actually taking the SNR into PNR, because when I take exponential, so this is diagonal D, so A is O inverse D O. Take the exponential of that. It will be a diagonal matrix with positive entries with the composition by O, right? So that will prove that this is in PNR. And next you notice that, yeah, so just like I said, so for all P inside P and R, uh, there exists a matrix in SO and R such that this is diagonal with positive entries. So therefore, so if this is equal to D, then you can write P as, so you take this O inverse D O, this is equal to P, but then D has positive entries on the diagonal, so you can take log of this, those things. So I'll just write that as log D. So P is exponential of that. This is symmetric matrix. Okay. So this follows. It follows that P is in the image of this. So this proves that the exponential map is surjective. It follows that exponential map from Sn to Pn is surjective. Okay. And lastly, I have to prove that it is injective. So injective will follow from the very simple fact that so if so all matrices in Sn are diagonalizable, right? So if A is a matrix, symmetric matrix, and lambda is an eigenvalue, of A with eigenspace V lambda, V sub lambda, that is the space on which A action is by scalar multiplication, lambda multiplication. Then when I take exponential A, then it has this eigenvalue e to the lambda. Then e to the lambda is an eigenvalue of exponential A with the same eigenspace. So two matrices A, B and S and R, suppose they are mapping to the same thing, then these eigenspaces will be same, and on those multiplication by scalar, that scalar will be same. So that will prove that this exponential map is injective. Okay, so this proves this. So bijection. So now you take two matrices A, B inside the symmetry matrices, and suppose they map to the same thing. So then they will have the same eigenspaces, E lambda. And those eigenvalues are of this form e to the lambda. So, yes, take the log and this with the eigenvalues of the original matrices. Therefore, it is same. Okay. So as I said, more precisely, this is a diffeomorphism. Maybe next time I'll show this. So you take any two matrices A, B, so exponential A times B times exponential minus A, this is equal to exponential of add X, add A. Okay, so given a matrix A, so you define this add A, which is a linear transformation, right, on M and R. And so this equality holds. Okay, it's quite basic. So proof is simple. So what you do is that proof What is that? Add. Oh, sorry. Yeah, so maybe I'll just define what is add. So add on any element x is simply xa minus ax. Okay. So I guess I'm using this one instead of the other one. So yeah, maybe I'll just, I think the other way. So this one I'll just write this as LAX minus RAX, where by LA I mean multiplication on the left by A, and this is multiplication on the right by A. So both of these are linear maps. And so add A is LA minus RA, or you can write this as LA plus R minus A. And since the left multiplication and right multiplication, they are commuting linear operators, it is very easy to compute the powers of this. So now, therefore, 1 by k. So I have to finally find this exponential of this. So 1 by k factorial, add a to the k. So this is maybe on b. This is 1 by k factorial, and this one, so LA plus R minus A to the k on B. Okay, and then you compute this. I said that they commute, so it is very easy to compute this apply binomial theorem. And okay. So this is simply we write m plus n equal to k, and then k factorial by m factorial times n factorial, and then LA to the m R minus A to the n acting on B, like this. Okay, and so yeah, so m and r positive, bigger than equal to 0. So then this becomes 1 by m factorial times n factorial, and this one is a to the m b a to the n, like this. Okay, so therefore you can compute the, so hence exponential of add a on b. This is summation k bigger than equal to 0, and then summation m plus n equal to k. This is 1 by m factorial times n factorial. Oh, sorry, yeah, minus. Thank you. Minus a equal to that. So this is minus 1 to the n. So this okay, and then I leave for you to check that this is equal to this right left hand side. So please check that. Okay. So next, lemma 2. So this, yeah, as I said, this will be something boring, but this is preparing us for proving that PNR is a Cartesian space. Okay, so lemma 2 is that suppose A is inside SNR, so symmetry matrices, then add A is self-adjoint. That is add A on X, so self-adjoint on M in R on the whole of. So this is a inner product on M in R. This is also very easy. Let me sketch a proof. So the left hand side is trace of add AX times Y transpose. And then I'll just write the formula for this one. So trace of AX minus X. And then you will use the fact that trace of any matrix is same thing as its transpose. So I'll apply that. So then this will imply that take the transpose of this. So Y times AX is X transpose. This becomes Y times this one. So A transpose and X this transpose. So that means X transpose times A transpose. But A is symmetric. So like this. X is symmetric. X. What is that? Oh, sorry. A. Sorry. You are right. Yeah, right. Sorry. This one, and then we have to come to this. I don't know. So finally, I have to reach here. So what do I do now? So I guess. So then I just use X transpose A. Like this, and then break this. This one. So now here, no. So I want A, Y, and then Y, right? So for this one, I'll use, so like that. So trace AB equal to trace BA. So YA times X transpose. And then again switch this one, maybe. This one to this side. So therefore, this is trace of AY X transpose minus trace of YA X transpose. So then we are done. So trace of AY minus YA like this, and this is add A on Y times X transpose. So this is therefore add A on Y inner product with X, which is the same thing as since it's symmetric. So okay, finally. This proves that this is self-adjoint. So next I'll try to prove this lemma. I think I don't have enough time. Let's see. So we define the operator tau x. So x is some matrix inside. For me, it is inside SNR. We define tau x from MR to MR by setting tau x of y is the derivative of this exponential minus x by 2 times exponential x plus ty times exponential minus x by 2. This one. Then this is self-adjoint. I mean derivative at 0. Thank you. So this is what I want to prove. So how do I proceed? So proof. So I just maybe I just finish this proof and I stop. Still have 5 minutes, right? Okay. So so this derivative, this one, at t equal to 0. So just push the ddt inside. So okay, at t equal to 0. And then expand this one. Okay. So try to expand this one. Okay. So by use the Leibniz rule, okay, repeatedly. So then this will become and then x to the m um, What is that? Yeah, so yeah, 1 by k factorial is there, so exponential. Like this. Okay. And so therefore, I call this, just keep it like that, call it star. So then note that this implies that tau x is a linear map. Okay. This implies. And then we'll try to prove that it is self-adjoint. We'll use this formula. And so now the inner product of tau x on y z. So this one is a trace of this huge thing. Exponential minus x by 2 times z transpose. So then what you do is that I move this to the end. So then this becomes trace of this one. Exponential minus x by 2 z transpose, and then again move this x to the other side. So then this becomes trace of y x to the n exponential sorry. This one. Okay. And finally, use the fact that exponential of minus x by 2 commutes with x. So therefore, this becomes so here. This one. So I'll write this as x to the n z transpose x to the m exponential minus x by 2. Okay. And I'll pull this thing out. So trace of y exponential minus x by yeah. So here m plus n equal to k minus 1. X to the n z transpose x to the n. This one, and then exponential minus x by 2. Trace of this whole thing, and then you come here, apply the star. So therefore, now apply the star, and so it follows that this is nothing but trace of y times tau x acting on z transpose. by star. Okay. And so now, finally, this is tau of x z transpose. It will follow from the start that if I replace y by y transpose, then I can just take the transpose of the whole thing, because x is in S and R. And so this, so what do I have to show? I started with this one. So therefore, I can just take the transpose of this. So this is tau x z y transpose. And so this is inner product of tau x and z. Y. Yeah. So which is the same thing as y inner product tau x. So this proves that this is self-adjoint.